switch off the yeah, as you remember, last lecture, I don't know where this feedback comes from. Doesn't help. So we have a really strong feedback here. I think you cannot hear me. Switch off this, but it's not you. Sure. Maybe now it works. I don't know. Okay, just we try it. So we used O'Shannon's channel coding theory. By means of the law of large numbers, basically showed that if we have a certain channel, and for the first we discussed a so-called discrete memory channel described by the conditional probabilities, as you remember, and certain message, and we encode this message and we add redundancy. Best case, we can extract a nearly error-free message, which is identical to the mutual information, multiplied by the number, of course, of symbols which have been transmitted. We have shown this by the law of large numbers. And then we said, if we now maximize the mutual information over the input alphabet, basically, so we may change the probabilities here at the channel input. If we maximize then this mutual information, then we obtain the so-called channel capacity. And I used here this symbol Imax to say, or to distinguish this from the channel capacity per time unit. So this is in bits per symbol, bits per transmitted symbol after the coding, yes? Oh, I'm not, this was missed, as always. Forgot this. Thank you. It's shared. For you. But you see this on the slides. Yeah? And a few seconds you should see this. And then we discussed this for a very famous discrete memoryless channel. This was the binary symmetric channel. So we only transmit binary symbols. We receive binary symbols according to this model. We have a certain probability of an error on this channel. And this is basically the probability that we don't have an error, so that we receive a zero if a zero has been transmitted. This would be no error. And we said it's quite easy to find here the mutual information. It only depends on this channel parameter, of course, PE. And then in order to obtain the maximum mutual information, we have to say, okay, then in this case, we need to maximize here the entropy at the output. And this entropy cannot be larger than 1 bit, of course. And this is only possible if we also have the same probabilities here at the input, so the zeros and ones have the same probability. Then in this case, sorry for this feedback here in the sound, of course, if we almost have no errors on the channel, our mutual information or our channel capacity is nearly 1 bit. If it's exactly 0, we don't have errors. This cannot be this microphone. We don't have errors, then the channel capacity is exactly 1 bit of this binary symmetric channel. If the bits are completely randomness received, with a complete random situation. So you could also use a binary dice to obtain the bits. then your mutual information and the channel capacity is exactly 0. For PE equal to 0. Of course, if the error probability would increase more and more and would approach 1, each transmitted 0 is received as a 1, each transmitted 1 is received as a 0, then again we have a channel capacity of 1 bit. Yes? Yeah? First, this is just, let's say, this is just a mathematical description. It's clear that if all the zeros are for sure received as a 1 and all the 1s are received as a 0, then there's no question about this. Then the channel capacity is just 1 bit. This is just a mathematical question. Then you could also say, I use a kind of training sequence in the simplest case, and I transmit a stream of known information. And then, let's say in this very simple case where it's just completely inverted, and then by means of this training sequence, you would know, in truth, I have transmitted a 0, but I received a 1. And always, if I transmit a 1, I receive a 0, then could detect this from this training sequence, for instance. Time referred? Yeah? Yes. Yes, of course. We come to this topic today. This is just, of course, the binary symmetrical channel. This is a time discrete channel. This is a time discrete channel. And for this time discrete channel, it's for sure you just generates zeros and ones. And the bit rate just depends on the time interval between these X samples here. So there is an underlying time interval, which we are not interested in this, because we started with a discrete memoryless channel. So it's time discrete, okay? Time discrete. And today we switch to time continuous, and then you will see the results which you find in books, okay? So that only if we have a channel, let's say, with a limited bandwidth or so, then we can say we have a restricted symbol rate. Otherwise, we don't have any identification of a restricted symbol rate. Just the rate of the symbols here at the end determines the bit rate, which is possible. So if the symbol rate, for instance, here, the input of the channel and at the output, if this is, let's say, 1 megabit per second, okay? But these are coded symbols. And let's say the mutual information or the channel capacity is just 1/2 bit per symbol. Then this 1 megabit of coded bits becomes 1/2 of a megabit of message bits here at the input. But we don't talk about this because we have no bandwidth limitation in this. It's just time discrete. But we have to switch to continuous time, of course. You will see, this is just the simplest way at the beginning. Then we said, we switched to a Gaussian channel, and again, we started with a discrete time channel. And as we switched to this additive white Gaussian channel, still time discrete in the last lecture, we first have to basically find a measure of the entropy for a random variable which has not a countable number of states. And we said this is the differential entropy. Strange. So if I move here, then it disappears. Then we said we call this differential entropy. We have done this in the seminar, as you remember. So I just write this down, and the most important thing is that if you have a second moment constraint, so an average power constraint, if this random variable where we measure the differential entropy is Gaussian distributed, then it achieves the highest possible differential entropy under this average power constraint. So there is no other distribution at this average power which leads to this differential entropy, okay? And this has led us to the conclusion that we found the capacity per symbol, yeah, of this discrete time Gaussian channel in the last seminar. And we ended up basically in expression, we ended up in this expression here. You remember from the last seminar, 1/2 log 2 of 1 plus, and this was what we referred as signal to noise ratio. We can shortly write this down. I just show you one further thing. If you want to prove the fact that the Gaussian distribution achieves the highest differential entropy for a given average power, you can start with this equation or inequality basically, which is Gibbs inequality, this equation here. Yeah, you just say, I believe that this inequality is true. And if you want to prove this, you can prove this inequality by this, basically, this upper bound x minus 1 of the logarithm of variable x. And you know, we measure the information content by the dual logarithm. So this x basically stands for our probability density function. Yeah, you can prove this equation by means of this approach. But once you have this approach, which says, look, you have a certain random variable y with a distribution fy of y. And then you have another random variable, let's say we denote this as x. It has the amplitudes, I still denote the amplitude values as y. Then you end up, according to this Gibbs inequality, you could say fy of y times log 2 of fy of y with a minus sign. What is this? This is a differential, oh, it's terrible. This is a differential entropy, yeah, of y, right? Then we end up with, then this differential entropy, according to Gibbs inequality, is lower than fy of y, so the probability density of y, times log 2 of fx of y. So this is this other random variable. And now we say this other random variable, let's say, is Gaussian distributed here. We know for a Gaussian distribution, we calculated the differential entropy in the seminar to be this expression here. So this is valid for x, okay? So we know this is valid for x. And we know this is just the entropy of y, the differential entropy. Now we insert this. So we say this differential entropy, which is this left-hand side of this Gibbs inequality, this differential entropy is for sure lower than fy of y times log 2 of our probability density function of a Gaussian distributed random variable, zero mean Gaussian distributed. Now if we calculate this, we insert this Gaussian distribution in the log 2. And now we can use the laws of log 2, yeah? We say here we have this product, so we write this as a sum, right? And then we end up with an expression where we see here, the first part of this expression is again power of y, not of x, of our random variable, it's the power of y. But we assume that y has the same power as x because we are interested in the mutual or the differential entropy at a given power. So y and x have the same power. This is really important. But y has a different distribution, not Gaussian distributed. But still, this is the power of y. Then if we end up with this expression, we say that the differential entropy, we just insert this distribution of x in this Gibbs inequality. And then we end up with a conclusion that the differential entropy of y is just smaller or equal than the differential distribution of our Gaussian distributed random. And it's only equal if it's the Gaussian distributed. So it's never larger than for this Gaussian distribution. You can try it at home if you want. Because this fy of y times y squared is just the power of y, which is the same as the power of x, because it's the same constraint. I just want to show you this very short. So, and then we said, okay, we switch to this discrete time additive white Gaussian. I don't know why in this week there is this strong feedback in the sound, and in other weeks there's no feedback. I don't know. So of course, always remember, yeah, even if you see pictures where this index here is skipped, we always transmit long sequences of symbols, yeah, or let's say in our model of random variable. Only if you have very long sequences, which means basically in the word very long code words, you can really up with a situation, yeah, where you can extract message bits with an arbitrary low error rate at the receiver after decoding. This is our model, and we ended up with this expression. And today, now we come to this question, yeah, what is with bits per second? We have to basically map a continuous time AWGN channel, which is also referred as a waveform channel, because any real-world medium which I can use for transmission, a copper cable, glass fiber, radio frequency channel, yeah, whatever, this is an analog medium. We can only transmit certain waveforms to represent our data, and this is what we need to do today. See what happens. How can we map this channel into this discrete time Gaussian channel? See what happens. Okay, let's do this. Just finish what we have written in the last lecture. So we ended up so we said, okay, here differential entropy, and this is where we want to continue, but this is quite simple, yeah. Basically have the results. So I copied this, yeah. Just continue, but basically we have derived everything in the last seminar. So differential entropy. So we write just let's consider a random variable. Consider, yeah, probability density function. Now we have to switch from the probability mass function to the density function, okay? Fx of x. And then we say the differential entropy. And you know there is a difference between the differential entropy and the entropy we have used before, yeah? Differential entropy is defined as, you remember, now we switch simply from the sum to an integral. And if the amplitudes extends from minus infinity to plus infinity of this random variable x, of course, then we have to say, wait, the information condenses. We still use this log2 of fx of x. Weights them with the probability fx of x times dx. Okay, and of course we need this minus sign. And this is just the differential entropy. So I cannot improve the sound, sorry. Chance for me. And you remember, if we compare this to the absolute entropy, there was this minus log2 of delta z, which was our basically resolution if we switched from a continuous distribution by means of discretization to discrete values. So take care if you integrate absolute values. Yeah? So, and now we say, okay, differential entropy of a Gaussian so you can say C seminar, yeah, to interpret this. Differential entropy of with zero mean. So we say just, yeah, that x is non-distributed with a mean of 0, let's say with a power px, yeah, which is the second moment. And then we end up with this expression, h of x. We have derived this in the seminar as 1/2 times log2 of 2 pi e, this is Euler constant, yeah, times px. Of course, only if it's zero mean. So we said, if we add a dc here, this has no contribution to the entropy. You remember from the seminar? So we inserted a Gaussian distribution with a mean of so this is, you could say, in bits per symbol, yeah? So, and now we can come to basically the channel capacity of such a Gaussian channel. Okay. So now dot 2, right? 2 channel capacity, and I write it again, yeah? Channel capacity. Because there was this question here from the student in the lecture hall, yeah, of a discrete time. This is really important. AWGN channel. So and now the situation is exactly as in the seminar. So we basically could skip this. So yeah, so we have a sequence, yeah, of random variables, and if I take a look at one of these random variables at the channel input, it's xm, and for some reason we add noise, which is discrete time noise. Yeah, we say this noise is, let's say, nm. So this is noise. AWGN, additive white Gaussian noise, as you remember. Okay? But everything is discrete time, and we receive y. We have to say this is basically a substitute channel. So our real-world channels are analog channels. And in the next section, I will show you how can these waveform channels, these analog channels, mapped to discrete time channels. This is what we are doing today. But we start with this because it's simple. Then we said this noise, yeah, is independent on the signal. Okay, this is really important. So x, m, and nm are statistically independent. Okay, and we say, yeah, the expected value of x, m to the square, let's say we denote this as px. So this would be the second moment at the channel input, or if you want, the power. So we have an average power constraint. Average power constraint. Or constraint. So this is our channel input. It may have a DC, but we will see when we don't get the channel capacity. So we basically define this is the power, of course. And then we say, if we take a look at the noise, we say the expected value of this is just, or now we can write this is just Pn, this is the noise power, according to this model. And since it's additive white Gaussian noise, independent, or these adjacent noise samples are statistically independent. So otherwise it wouldn't be noise. So we could also say expected value of Nm times Nm plus a certain value k is just 0, 4 to 0. Two different samples. They are statistically independent. Now we say we know this noise is Gaussian distributed. This is where this G comes from. It's Gaussian distributed. This white means basically this expression at the end. And then we could say that the differential entropy of our noise. Now I skipped this time index because it's independent on the time index. Of this noise is just 1/2 log 2 of 2 pi Pn. So times this noise power. That's clear. And then we said we need to calculate the differential entropy, but conditional differential entropy of y. Y given x. So we need to calculate this. You remember this was the irrelevance. Denoted this as irrelevance. And then we could say, okay, this is the same as h of x plus n, because y is x plus n, it's an additive channel, given x. And of course, there is no surprise in x if I know x. So this is just equal to h of n given x. But x and n are statistically independent, and therefore this is the same as h of n. This is a very simple proof. So now we have this irrelevance, okay? And now we take a look at the mutual information, of course. And mutual information, for the mutual information, we need to calculate h of y. So how can we do this? The maximum value of this h of y gives us the channel capacity because the irrelevance is fixed. So we need to look to search maximum of h of x for a given px. So our transmit power is just px. As we said, this is our constraint. And we can say, since py is equal to px plus pn, why can we write this? We can write this since Pn is zero mean. You remember there were seminars where we proved this. If we have two random variables and we add them, we can add the powers if at least one of the random variables is zero mean. You remember? It was quite simple to show this. So this means Pn is fixed. This describes our channel. Px is fixed because this is our average power constraint. Then we know Py. And now in order to maximize the mutual information, which is just h of y minus this, we have to maximize this. The maximum value is given for a Gaussian distribution of y at this power. So therefore, y needs to be Gaussian distributed. Then we can write is equal to 1/2. So this is our result, log 2 of 2 pi. What is the received power Py? But we write this as Px plus Pn, since the noise is statistically independent from our signal. This is just Py. And therefore we get I max is basically given as the mutual information for the input, for the channel capacity approaching input distribution. So it's basically, it's equal to the maximum value of I, of the mutual information, over all possible distributions of X. And we know this value is at least given if Y is Gaussian distributed. Then the value is, now we take the difference of this and this. So we have a difference of 2 logs. Then we can write this as 1/2 log 2. And then instead of a difference, we write the quotient within this logarithm. And then we become Px plus Pn divided by Pn. The other terms cancel out. This is, of course, can even simpler be as this, log 2 of 1 plus x divided. So this ratio of the signal power compared to the noise power determines this channel capacity per symbol. Yeah? So in bits per symbol. Of course, we know, yeah, if y is Gaussian distributed, and if the noise is Gaussian, or needs to be Gaussian distributed, and if the noise is Gaussian distributed, then x also needs to be Gaussian distributed, because only the convolution of 2 Gaussian distribution, as a distribution function of a Gaussian random variable, give a Gaussian distributed. We even proved that if you have a sum of 2 random variables, yeah, and they are statistically independent, yeah, then the distribution of this sum is the convolution of the distribution functions. So we know x also needs to be, of course, zero mean, that's clear, and Gaussian distributed. Then we have channel capacity. Of course, yeah, the result depends on x divided by Pn. Ja, and it's interesting, yeah, if for instance Px divided by Pn approaches 0. So you have basically a huge amount of noise and only a very small signal power. What is log 2 of 1? 0. And the channel capacity approaches 0. So and now you can insert different values and obtain some result. And now we come to the more difficult part. Now we have to map continuous channel into a discrete time channel. Unfortunately, we have not all the background to understand every step. I try to do this now, and probably at the end of the semester, if we learned about modulation schemes in communications engineering, matched filters in communications engineering, signal space thesis in communications engineering. I do one further lecture and come back to this model here, show here. But I think the major things can be understood. So I write here 5.3, yeah. And now we discuss an ideal and limited continuous time yes. Yeah. Yes. We've shown this. If you remember, there were two dice, and we take a look at the sum. And then we said, if we know one dice is equally distributed between 1 and 6, the other also equally distributed, okay? And the sum number, which is the result of the first dice and the second dice, this was such a triangular distribution in the seminar. Convolution of two rectangular gives a triangular. Now the convolution of two Gaussian gives a Gaussian. This can be proven in the frequency domain if you fully transform. So ideal band limited continuous time AWGN. Yes? Take care. We just have this constraint. Yeah? We have a constraint where we say x, yeah, has a power of px. We don't know anymore. Yeah? And then we started to develop this. And we said, okay, this is a irrelevance. And then we said y needs to be Gaussian distributed in zero mean. Only in this case, yeah, we get, of course, zero mean, because we know, yeah, we know if we add a DC, there's no contribution to the differential entropy. And then, as we said, y needs to be zero mean and Gaussian distributed. And the noise is zero mean and Gaussian distributed. For sure, x is also zero mean and Gaussian distributed. Not only Gaussian, this is not enough. It needs to be zero mean. So y is also zero mean, of course. Because only the zero mean Gaussian distribution leads to the highest differential entropy at a given average power constraint. It's a zero mean Gaussian distribution. Otherwise, this equation is not valid here, what we wrote here. Because then you need to insert the variance instead of the power. So AWGN channel. And now, what is the situation now? Basically, start with the mapping. So what we know is that we want to transmit a sequence of symbols, of course. It's like this, maybe. Let's say we start with, or we just insert one further hint, yeah, and this we assume here that a continuous frequency band in the real world, so only take a look at positive frequencies, yeah, starting at f to 0 is available. We assume a brick wall characteristic, channel characteristic. So this is where this bandwidth limitation comes from, channel characteristic. Yeah, but I come back to this in a few seconds. And now we take a look, say, we make a small subsection and denote this as real pulse amplitude modulation. Yeah. Real pulse amplitude. But again, yeah, this is the topic in communications engineering. So we have a lack of background. But let's say we do the following. We want to transmit a sequence XM, write this like this. Yeah. Sequence of XM as before. Yeah, this is a discrete time sequence of random variables, so what we refer as a random process. But now we say, what is it? XM, each XM, yeah, say each XM. XM, so if you take a look at a certain symbol, is a real modulation symbol representing data. So this represents our data at the output of the encoder to be transmitted. Each XM represents real, not complex data. So, and we do this by assigning a certain waveform. Because we have to transmit a waveform. So, assign a certain waveform. And we denote this waveform, let's say, as psi1 of t. There's only one waveform in our case. Yeah? We assign a certain waveform to each XM. So the transmit signal, the continuous wave transmit signal, yeah, continuous time transmit signal. So the continuous time Tx signal is, now rewrite this, it looks like this. This is the general form of a pulse amplitude modulated signal. So we have pulses, psi of t, okay, and the pulse amplitude is modulated by our modulated symbols here, xm, to be transmitted. Each xm represents data. We can say it's a modulation symbol, yeah? Modulation symbol. Okay, now we can write this transmit signal, which is continuous time. Sum, m goes from minus infinity to plus infinity. Now, maybe I write here a lowercase, yeah, letter to say this is a concrete sequence. Otherwise, the transmit signal would be also process. Yeah. Just want to say this is a concrete sequence, xm, and these values weight this concrete signal waveform, this waveform. Then we generate, and now we come to symbol interval, we generate this waveform according to the modulation interval. Yeah? So minus m times capital T. And capital T is the modulation interval. So this is the time interval, yeah? Where the basically a new modulation symbol is generated. Okay, so T is the modulation interval. It's not the rate, but it's the modulation interval. It's basically the interval also of the symbols at the output of the encoder. Yeah, it's just the modulation interval. You could say 1 by capital T, yeah, is the modulation or symbol rate, but we define this as modulation interval. Okay. And you see, we generate these psi's, yeah, with each new interval and weight this amplitude. Therefore, this is amplitude modulation, yeah. Pulse amplitude modulation, as we wrote here, T. And the symbols which modulate these amplitudes of these pulses, this is important. And now we have to further say the waveform psi1 of t has to fulfill the following condition. Fulfill, or has simply the following, is the following heuristic. So this is really an important characteristic. Integral from minus infinity to plus infinity. Psi1 of t times Psi1 of t minus, let's say, a times t. You remember what this capital T is? This is the modulation interval, dt. Here we assume, the first thing is just an assumption, yeah, that this is 1, okay, for k equal to 0. So now we basically compare, if this k is 1, for instance, we compare two adjacent pulses, right? And we need to have the following condition, that this correlation between two adjacent pulses needs to be 0. This is just a correlation, what you see here, scalar product. So this means they are independent. So this is 0 or k to 0. And this characteristic ensures, this is just, these pulses have unit energy. This first characteristic, because you can see here psi1 squared of t dt. This is just the energy of the pulse. Energy of the pulse is, in our case, 1. Okay? But this characteristic, this 0, ensures that there is no intersymbol interference between adjacent symbols at the output of the optimal detector. This is what we have to say. So this ensures no intersymbol interference. This means, ISI means intersymbol interference. Yeah? This means, yeah, that adjacent symbols at the receiver, at the output of our optimal detector, are statistically independent still, this characteristic. So this is still a memoryless channel. There is no interference between symbols at the receiver. ISI, the symbol, interference. But we discussed this in communication engineering. Okay. So, and now we basically discussed the modulator, but we have to talk about transmit power, or let's say transmit energy per symbol. Now we can discuss this. So this is a characteristic of our transmit signal. Now we know the transmit signal. Yeah? We modulate certain pulses depending on our data. But this data is not just 1, 2, 3. It's normalized. Yeah? It just represents our data to be transmitted. Now we say mean energy let's start with this energy of an isolated Tx pulse. We just consider one pulse isolated and want to measure the energy. What would be the energy? Then we could say this is, let's say it's this, integral. This is an isolated impulse, yeah? Integral from minus infinity to plus infinity. So we weight, let's say here we have xm times c1 of t minus m times t. But this is just one m, one isolated pulse, the mth pulse. Could be m could be 0, for instance. dt, and this to the square. This is the energy, right? So I could say the system theoretic energy. So if I square this, and if I square this, I have the energy. And then you see the energy of this isolated pulse, number n, with time index m, yeah? Or m. So this is the time index of this pulse, okay? So this is just xm to the square times 1. Because we assumed a pulse shape which is unit energy, just for simplicity, okay? So our pulses which are modulated in the amplitude have an energy of 1. So basically this xm contains the energy. So this is not unitless, it has an energy. Therefore we could say mean energy of each tx symbol. How could we measure this? Then we could say this is just, and we denote this as ES, yeah? This is the mean energy per, let's say, per tx symbol, we write per of each modulated symbol, pulse. How large is it? Then we have to say, we have just to take a look at the expected value of xm to the square. This is now the mean energy per symbol, okay? So this is not the power. We referred this before, as you remember, expected value of the random variables at the channel input. This was a power, you remember? But you could say, okay, instead of power, I use second moment. Yeah? And now this is really an energy, because we have this expression. Now we included the pulse, and the whole pulse has an energy. And then the next step is, what is the mean transmit power? Tx stands for transmit power. You remember, yeah? What is power? Power times time is energy, right? So this means power is energy divided by time. So the mean transmit power is therefore Px is equal to the energy in the symbols, Es, mean energy in our transmitted modulated symbols, divided by the according time interval. Right? Now we have the relation, yeah? We say the expected value, what you can see here, of these modulated symbols is just the energy per symbol interval, per modulation interval. This means the mean transmit power is just this energy divided by capital T. And capital T is our modulation interval, right? I think you can understand this until now, I hope. So we can use here, this is an important equation. And this before is also important, of course, this equation. Now we have it. And now, how does the channel look like? Channel, yeah. Channel. Channel. Without band limitation. Without the band limitation, how does it look like? Now we have a transmitted signal, concrete transmitted signal x of t. We have additive white Gaussian noise, and this is continuous time. Additive white Gaussian noise, what you see here. And then we have a received signal y of t. A received signal y of t. And this n of t, this is our AWGN. Additive white Gaussian noise, but continuous time, as you see, of t, right? So we know it's Gaussian distributed, but we cannot say, we cannot talk about the noise power because this depends on the bandwidth of our receiver. So we assume that this white noise, yeah, this means at any frequency we are looking, measure the same power spectral density. Okay? So we have to statistically describe the noise, and this is what we are doing in communications engineering currently, but we started with discrete time random variables. Now we switch to continuous time random variables and basically take a look at the Fourier transform of the autocorrelation function. This is the power spectral density. And here we see the frequency f. And if we measure the relative power of the noise at a given frequency, we always have the same relative power, which is power spectral density. So this is the power spectral density. I write it here, power spectral density. And we usually use this symbol here. We do this tomorrow in communications engineering. Fourier transform of autocorrelation function. We use this capital Phi. And then here I use this capital N to say it's a process. But I'm talking about the power spectral density of the noise. And this depends on the frequency f. Okay, and now this may look a little bit strange, what I wrote here. There is a parameter which describes the noise. And this is n naught by 2. So what I've shown here is the two-sided power spectral density. And the real-world power spectral density, if the frequencies would be only positive, is n naught. Understand? We use here for Fourier transform always the two-sided Fourier transform. Therefore, we have negative frequencies and positive frequencies. In the real world, we always have positive frequencies. And if we measure the real world power spectral density only for positive frequencies, we get a value of n naught. So n naught is the technical, this means we have only right-hand side frequencies, yeah? Power spectral density. This means only positive frequencies. So if you draw it only for positive frequencies, yeah, only positive frequencies, you have twice this value for the two-sided. So if we take a look at a certain power, you don't have to draw this. If we take a look at the power at a frequency, let's say f1, in this, we have also to take a look at minus f1, and the total power in a certain bandwidth range, yeah, would be this. Take a look at the right-hand side, delta f. The total power at f1 in a band of width delta f is delta f times n naught by 2 times 2. See, this is n naught by delta f. So the power spectral density times the bandwidth, where we measure this power, yeah, is just n naught times delta f. Therefore, this is the technical power spectral density. So this is our channel now. And later we assume that our signal has to fit in a certain Brickwall characteristic. But this is at the moment not so important. So if we take a look at the Fourier transform of the transmit signal, we have a strong bandwidth limitation, yeah? But we don't need to consider this at the moment. Now we have to take a look at the receiver. And again, there is one step missed. Yeah? So this was real pulse amplitude modulation. This is the channel, let's say. So I skip this and make this maybe large channel. And to say this is like a subsection, okay? And now I say optimum detector. So in the optimum detector looks like this, yeah? Now we receive our signal Y, okay? And now we have to use, there are a Y of t, of course. This is a continuous time signal. So, but this is interfered by additive white Gaussian noise. And this noise is described by a power spectral density. It's not a power, it's a power spectral density. Take care, yeah? And now we receive the signal, and how can we extract, in the best case, something like the modulated symbols? Way is to use a so-called sampled matched filter. So, and this consists of first of a matched filter, and the impulse response of this filter is G of t equal to, I assume here, non-causal filters, psi of minus t. This has something to do with optimal detection. And we will discuss this in communications engineering, okay? But we need to use such a filter or a correlator equivalent. So this is just a filter. This is the impulse response of this filter. G of t matched filter impulse response. Why is it matched? Because this impulse response is matched to the used waveform, right? It's matched to psi1 of t. So we use certain pulses, psi1 of t, and we match our impulse response exactly to this waveform. So we can write here matched to psi1 of t. Therefore, it's denoted as matched filter. The main purpose of this filter is to collect the energy as in the best way of the received pulses and to reject noise in the best way. This is the purpose of this matched filter. It gives the best possible signal to noise ratio at the sampling time. So now we sample the output of this filter. So this is the filter, yeah. The matched filter. And what comes out needs to be sampled, and we know, of course, the sampling interval, and this, so this should be a sampling device. Yeah. Now I sample the output, and the sampling interval here, this is just, so we sample here. The sampling interval is m times capital T. So we encode our information on these pulses with the modulation interval capital T, and then we observe the output of this matched filter at the interval capital T, right? The same interval. So this means if we transmit the first symbol, so this is the weighted version of psi1 of t, the receiver makes a convolution with psi1 of minus t, and then we sample the output. Okay, and this gives at the end the if we reject the noise, yeah, there's no noise in this, just at this in this moment. We sample basically the autocorrelation function of this pulse psi1 of t. So, and if we would write down the convolution of the transmit signal with this matched filter impulse response, okay? And then we end up basically in parts of this convolution which look like this, because let's say we transmit a pulse at the time, this is the pulse train, this is the pulse train, then we could insert here M if you want, and this is the matched filter impulse response. But if you do the convolution, yeah, you know in the convolutional integral you have to insert one signal with a negative time index. So this psi1 of minus t becomes psi1 of t in this convolution. And this condition, what is written here, ensures that at the output of this matched filter, adjacent pulses, so I don't talk about noise, that adjacent pulses do not interfere. So what we receive here, let's denote this as Ym. And now you understand. Look, we transmit Xm, is it? We transmit Xm here. Okay. If you want, you can draw a figure for one symbol. It looks like this. Just for one, it's Xm, certain value to be transmitted, and we assign a certain pulse shape, C1 of t, C1 of t minus m times capital T. Yeah? And this is one modulated pulse, an isolated pulse. But of course, we transmit a sequence. And now we transmit Xm and we receive Ym. Right? This is what we obtained until now. So now we could say, I know there is a missing step, but we can basically complete this theory in communications engineering. Now, if we assume n von t equal to 0 for the first, we just switch off the noise. It's not interesting, of course, then we have entropy, which is equal to the entropy of our input symbols. That's clear. Yeah? But this is just to understand what happens. If we assume n of t equal to 0 for the first, we get Ym. So let's say this is a concrete value here at the output of this sampled matched filter. Okay, we this here as this is the sampled matched filter, matched to the used pulse shape, sampled. This is just sampling. It's the same interval where we encoded or where we modulated our pulses. So now look, without noise, get this. This means our received symbols look exactly as our transmit signals. And now look, what do you think what happens if we switch on the noise? This is where we are interested in. Yeah? We get Ym is equal to xn plus m. M index is m, okay? And xm plus the noise, a sampled version of the filtered noise. So it's a linear channel, yeah? And we get basically, with each sampling here, we get noise additionally to the signal component. So sampled noise, but it's also filtered. So NN filtered and sampled noise. Now you see, what is this? This is our original discrete time channel, as you remember. So it looks like this. Xm plus nm, if I write this as random variables, yeah, and not as concrete values, gives Ym. This is exactly what we got. But we have to talk about this. How is the statistical description of this still Gaussian distributed noise? And now the thing is, the noise parameter of our channel, yeah? So this is the channel, this is the power spectral density and nothing more. And now if we use these unit energy pulses, take care, the real world, yeah, a filter has never a unit energy impulse response. The impulse response has a unit. It's in hertz, measured in hertz. But here assume, to make it as simple as possible, yeah, we assumed a so-called unit energy filter. This is not a real-world filter, but it's good for modeling. And even more, this filter is not causal. It's anti-causal, yeah? It's not causal because I just simply wrote C1 of minus t, okay? But if we do this assumption, we get statistics, okay? This is really important. Statistics of NM. So I switch between lowercase and uppercase, you know why. NM is concrete, a concrete realization, concrete value. No? And if I talk about statistics, I assume model is as a random variable. What is it? Since we use a unit energy filter, we can say the expected value of NM times NM plus K. This is just, so there is, you see again, there is a shift here in the time index. This is just equal to the noise power spectral density. The second moment, yeah, of this noise is equal to this noise power spectral density for K equal to 0 and 0 else. Again, this characteristic, this 0 else, just comes from our required characteristic for this pulse shape C1 of t. Because we said, if we do the correlation product between C1 of t and C1, and the shifted version here of this C1 of t needs to be 0 if this shift between the pulses, between two pulses, adjacent pulses, is exactly one modulation interval. Okay? So we said this is 0. This ensures that this is now our noise model. This is discrete time AWGN, as before. So this is discrete time AWGN. Now we have everything. Because now we know X and N are statistically independent. The signal is statistically independent from the noise. Okay, and then we can say, now this H of N, this, maybe we write here of N. The differential entropy of each noise sample, how large is it? It's 1/2 log 2 of 2 pi e second moment of the noise. But now this is a little bit strange. It's a noise power spectral density. Why? Because our parameter, which describes the channel, is a power spectral density and not a noise power. So, and this is equal to h of ym given xm. You remember we had this before. This is the irrelevance, so we already know the irrelevance. So now we have to take a look at h of, let's say, ym, just to say now we talk about discrete time. We are back at discrete time. What we have solved now, we have mapped the continuous channel, the real-world channel, into a discrete time channel. So, and this is, of course, 1/2 log 2 of 2 pi e. And now remember, n naught by 2 is the power of the noise. And the second moment of our xm, this was this, the energy per modulated symbol. This is the second moment of xm. Okay? So we now can say plus S. You remember ES, yeah? This is the so-called symbol energy, yeah? But we talk about modulated symbols, yeah? After this modulator, what is the energy in one modulated symbol on average? Average? G symbol. So we switch from a signal power and a noise power in the previous chapter to an energy let's say we measure an energy in watt seconds, and a noise power spectral density, which is also measured in watt per hertz, which is watt seconds. And now we can put this together and say, therefore, yeah, I max, because we can obtain this only if it's Gaussian distributed, of course. Yeah? And again, I have to write this here. Only if y, okay, is 0 mean Gaussian distributed. Right? Otherwise, we don't get this equation. And we know for any other second moment, we get a lower h of y, right? So now we can say, therefore, say we switch to red color, channel capacity, a symbol still. What do we get? We get I max is equal to, now again, we divide both expressions and get 1/2 log 2. You remember h of y minus h of y given x. And then we get here 1 plus energy per symbol divided by n naught by 2 symbol. Okay. So this was the starting point. Now we can ask the question, and then we have to assume something regarding the channel. Now we assume that our channel has a brick wall characteristic and ask for the highest possible rate of modulated symbols. So if one symbol contains an information of this and this number of bits per symbol, how many symbols per second can we generate? So, and this is the next question, basically, and this is highest symbol rate for baseband channels. So we don't take a look at bandpass channels. For baseband channels, base channels with a brick wall characteristic. This is the next subsection, basically. Now our channel looks like this in this model, and this is exactly the question from the beginning of this lecture. Now we assume that our transmit signal needs to fit in this spectral mask, let's say. So we have a spectrum which may extend, from 0 to capital B in the real world, yeah. And in our two-sided description, yeah, we use it from -b to b. But in the real world, yeah, say this is a transfer function of a channel, not of this filter, yeah, it's the channel. And this channel allows transmission between 0 Hertz and the bandwidth B. Therefore, this is called brick wall. This characteristic, this is the brick wall. So it's like a step function in the frequency domain. So in our signal should fit in this brick wall characteristic. And then the best waveform, which allows the highest transmission rate, is the best theoretical. Cannot approach this in practice. waveform C1 of t is, for this channel, let's take a look, switch to blue, looks like this. So first I write it in the time domain, it's like this. First I draw it in time domain, then I draw it in a frequency domain. It's like this. So first I draw here, this is T and here is F. Here this is the Fourier transform and this is our pulse. So this is C1 of T. And this is just a sinc pulse. So this is a possible waveform which exactly fulfills this characteristic. It's a sinc pulse, sinc function. And here we see exactly t, minus t, 2t, and so on. And here we would have 1 by square root of t. But this is not important. Important is that the zero crossings are exactly at multiples of our symbol interval, of our modulation interval. This means if we transmit this or this symbol with index 0 and then the same function but shifted to the right for the symbol with the index 1, there is no interference at the sampling times, the output of this matched filter. And the transfer function now looks like this. Not the transfer function, the Fourier transform of this pulse shape. This is the Fourier transform of this pulse shape. So it exactly fits into our channel, right? And you see, if this is capital T, this, our modulation interval, so how large is this? This is 1 by 2t, right? And this 1 by 2t, if we have a bandwidth limitation of B in the real world, so between 0 and B, this is real world, this is system theoretic, we can say that the highest rate of our symbols, or let's for the first write this like this. 1 by 2t is equal to, now I made some mistake here. 1 by t, right? Here is a sinc function in the time domain, sorry. Here's a sinc function, the zero crossing is at t. And the total width of this pulse is 1 by t, right? Yeah, this is the Fourier transform here, what you see here. And the total width of this rectangular pulse is 1 by t, not 1 by 2t. This was nonsense. Now I can say 1 by t is equal to 2b. This is what we wanted to achieve because 1 by t is just the rate of our modulated symbols. And this is the highest rates possible for this brick wall characteristic. There is no higher transmission rate possible because then you need more bandwidth at this bandwidth. So this means this equation here gives the highest symbol rate for a given bandwidth B. The symbol rate is twice as large as the physical bandwidth. So this is the physical bandwidth, the right-hand side. The highest transmission rate is rate for a brick wall channel with physical bandwidth B, yeah? Or let's say technical bandwidth B, is 1 by t equal to 2b. And now we have our equation for the channel capacity of such a brick wall channel in bits per second, because now we can say the channel capacity in bit per second is just our symbol rate What is the rate where we generate these modulated symbols? Times 1/2 times log 2 of 1 by divided by 2. This is in bits per second. Okay? Of course, I can write this as a function of the channel parameter B. And the channel parameter here, 1 by t is 2b, so we get b times log 2 of 1 plus s divided by n naught 2. Let's say we make here, say this is very important, write it like this. And now you may say, okay, n naught is really the parameter which describes our channel. Nothing else, because it's a power spectral density. But if you want to say, but n naught is a power spectral density, it's not a signal power, noise power. ES is an energy. Everything is fine, and we will see later that if we talk about modulation schemes, the bit error probability in the real world depends on the ratio of energy and noise power spectral density. So this is the correct measure. But let's one step back and let's rewrite this equation. We know that we can say ES can be written as the mean transmit power, right? Divided by capital T, so the modulation interval, times. So energy is power times time. So this means the energy in the modulated signal symbol is the mean transmit power, this is an average value, times the modulation interval. Now look, the modulation interval is 1 by 2b for this brick wall characteristic. So we could say, if we use a waveform which is identical to the one in the figure, which is the extreme case, could say this is equal to px times 1 by 2b, right? And now we insert this in the original expression, and what do we get? Capacity in bit per second would bandwidth times log 2 of 1 plus, and now we get an expression where we see the transmit power, because we can substitute this energy per symbol by the transmit power, px, divided by n naught by 2 times 2b, which is n naught, the physical or the technical noise power spectral density times the bandwidth. Still bit per second. But now we inserted a transmit power and a bandwidth. And of course, in our old model, this would be the real-world noise power for a bandwidth B would be n naught times B. So, and then we are back at the old model. Transmit power, mean transmit power, and mean noise power, real world. But still, this expression is absolutely fantastic because the channel parameter of the AWGN channel without this bandwidth limitation is just n naught. Yeah? And this rate, this depends, so this equation is only valid if we use this sinc functions for transmission. Otherwise, we cannot use this B. So, and now it's interesting. We could now develop a very famous limit for transmission. And the question is, can we reduce our transmit power more and more? Or does it help to increase the bandwidth more and more? Now look, if we increase the bandwidth more and more, we get, according to this transmission model, which is true, yeah, we get more and more noise, right? Because the noise scales linear with B. This means the signal to noise ratio, if we increase the bandwidth more and more at the same transmit power, we have a fixed transmit power. then the signal-to-noise ratio becomes lower and lower. We end up log2 of 1 is just 0. Of course, if we increase the noise, the bandwidth B, we can increase the transmission rate, but this term goes to 0. So it means it doesn't help to increase the bandwidth more and more at a given transmit power, so you don't increase the channel capacity if you further increase the bandwidth more and more for a fixed transmit power. It doesn't help. This is what is shown in this equation. But we can even take a look at a different thing, and this is the well-known required energy per bit level, energy per bit to noise power ratio. Now let's say this is basically the highest bit rate which is possible at an arbitrarily low error rate, right? This capacity, bit per second, yeah? Let's write this here, highest free or near message bit rate. If we talk about bit rate, it's always the message bit rate. And we know already, again, that at the transmitter, we need Gaussian distributed symbols. Highest error-free bit rate. Always talk about, then at the end, message bits. Let's say we denote this as RB. I mean, I know this is the same as B, but now let's say we write simply bit interval, which is the reciprocal value of the bit rate. This is the bit interval. The bit interval, yeah, is basically, okay. And if we take a look at this bit interval, which is the reciprocal value of the highest bit rate, we could say the energy in one bit, message bit, is just the mean transmit power times this bit interval. Energy per message bit, yeah? But we don't say this message. In reality, we always, if you take a look in books, yeah, you always say this is the energy per bit. This is just energy per bit, nothing more. But it's always related to message bits. And now you could say this is Px divided by Rx, right? It's the same. So, and now we could say RB max divided by B. Now take a look at this. I put this B at the other side. So this is the ratio of the highest bit rate, which is the same as the channel capacity. Just want to show this expression. It's equal to log2 of 1 plus. And now we substitute Px by this EB. Because here we have this Px. And now I can write, instead of Px, I can write PEB, yeah, times RB max. So I could say this is the same as times, or let's say divided by N naught, this is this, times R divided by B. This is an interesting expression because now we could say by N naught, you can just solve this equation here for EB by N naught. And you get a certain expression. See slides. So you can obtain the required energy per bit to a noise power spectral density. The noise power spectral density describes the channel, and EB describes the energy which needs to be put in one message bit. Reality. So everything is fine. Watt per second, yeah? Watt per hertz, watt seconds, same unit, it's unitless, this ratio. And the minimum ratio is 10 times log 10 of EB by N naught is nearly minus 1.59 dB. For E to infinity, what happens? or let's say, let's write it like this, 4 B divided by RB, very large, very, very large, let's say to infinity. So if we use a huge bandwidth, and we want to transmit a certain data rate, but our goal is not to transmit the highest data rate. We want to transmit with the lowest possible energy. And therefore, we spend a lot of redundancy, of redundant control bits, okay? So this means if we can spend a lot of control bits, we are not interested in a high bit rate. So we spend a lot of bandwidth for transmission just to add a lot of redundant bit to our message bit. Then we need more bandwidth. And then we end up at a required EB by NOT ratio, which is minus 1.59 dB. This is a well-known limit for transmission. So you can basically obtain error-free transmission at this level, but not below. This is a famous limit of Claude Shannon for transmission. And on the slides, of course, if you take a look at the slides, you can see here, again, this whole theory of how does the receiver, this is the pulse amplitude transmitter, this is a correlator equivalent of this matched filter, okay? It's the same as we discussed here, but differently realized, okay? Slides. We get this in communications engineering. So, and then we end up here, this is this expression, EB by N naught, which I mentioned, depending on RB max by B. You can insert values, but the minimum value, if basically this B approaches infinity, if we have a huge bandwidth for a certain data rate, then we end up in minus 1.59 dB, and this is shown here. So this is basically the ratio. It's also referred as spectral efficiency. So this is the data rate, the channel capacity, the highest data rate at a given bandwidth. And this is the required energy per bit to noise power ratio. So, and if the ratio, let's say, between the bit rate and the bandwidth is, let's say, 0.1. So the bandwidth is 10 times larger than the bit rate, about. We are very close to this minus 1.59 dB, EB by NOT ratio. If we have a bit rate which is equal to the bandwidth, the channel has brick wall characteristic. Then we end up with an EB by NOT which is nearly 0 dB. And then if we further increase the bit rate at a given bandwidth, we need more and more power. This blue curve, this is if we use Gaussian distributed modulation symbols. So we need more and more power. And now let's say, and then we finish, because this is communications engineering to a large extent. Let's say in the real world, we don't want to transmit with Gaussian distributed amplitudes, because this is hard to achieve. Let's say we start with just binary transmission. So we only use 2 amplitudes at the transmitter, 2 amplitudes. This means our mutual information per symbol can never be larger than 1 bit because we have only 2 symbol states at the transmitter. This means if we have a rate which is 2B, we end up with a bit rate which cannot be larger than 2B, because if the mutual information is nearly 1 bit per symbol, okay, this is the highest mutual information for a binary alphabet, cannot obtain more than 1 bit. And if we transmit this 1 bit with a rate of 2B, then our bandwidth, our bit rate is 2B. This is this. This is 1 and this is 2. So this is binary transmission. And of course, if the noise is large, so if we don't have enough energy per bit, bit rate is lower. So, or on the other way, if you describe it like this, if you make the bandwidth much larger than this bit rate, you can decrease the energy per bit. But you can never obtain a bit rate which is larger than 2B for binary transmission. If we switch to 4 amplitudes, you can never obtain a mutual information which is larger than 2 bits per symbol. And 2 bits per symbol multiplied with a rate of 2B gives 4. So this means the bit rate for this 4-level pulse amplitude modulation cannot be larger than 4 times B. It's here. But the interesting thing is the theoretical limit at very low bit rates, which means you have a lot of redundancy or coding, can still be achieved if you have a binary distribution. And this is often used. So if you are interested to transmit at a very low transmit power or energy per bit, you just use binary transmission. So you can deal with a lot of noise, and you could say there is no benefit to spend in more transmit amplitudes than 2 if you have a huge amount of noise. So if you transmit at a very low transmit power. Therefore, you can attain this limit, this minus 1.59 dB, nearly even with a bipolar distribution at the transmitter, not with a Gaussian distribution. You don't need this. But if you further increase the bit rate, you need more levels for transmission. For instance, if you use 16 equally distributed levels, equally distributed, not Gaussian, you can transmit 4 bits with each symbol. In the best case, if you have low noise, and 4 times 2 means 8. And you see here is a gap between the Gaussian distribution, blue, and this equally distributed signal alphabets, which are real world in most cases. And there are even approaches to close this gap, and this is called signal shaping. But this is just as real. And I can tell you just as a conclusion, we have now codes which are very close to this minus 1.59 dB for binary transmission. But it's much more difficult to obtain with real-world coding, to obtain these limits described by the Gaussian distribution at high SNRs. So high SNR coding is much more difficult. A lot of codes which you will learn in Marco Henhöfer's part are just binary codes, not multi-level codes which are combined with modulation. This is not so trivial. So if we talk about channel capacity approaching codes, then many people just talk about this region. That's all. Because next lecture is on Thursday with Marco Henhöfer. There is this new topic, error correction coding. Now you discuss real-world coding schemes. Yeah?